Hello everyone, I'd like to welcome you to Computer Graphics Rendering. In this video we're going to talk about any-hit shaders, shadows, and participating media. As a quick overview, we're going to review what the ray tracing pipeline looks like in a real-time ray tracing context, talk about how we can use shaders to handle hits along the path of the ray, and then talk about how we can incorporate shadows using any-hit shaders, and discuss how we can use participating media to make our computer graphics more interesting. So let's go over the ray tracing pipeline by review. It all starts out with ray generation. In this case, we may want to start from a camera, from a surface, and we want to go ahead and start by tracing a ray. And we do this by going through an acceleration structure traversal. So maybe we're using a voxel grid or some kind of digital differential analyzer or an octree or some sort of data structure that allows us to quickly go through all the objects in our scene. Well, once we found an object that we would like to test for intersection, we use an intersection shader. So maybe we're doing ray sphere or ray triangle. After we've determined there is an intersection, then we can call it any hit shader. And this is what the purpose of this video is about, and we're going to talk about that in a little bit. But once we've gone through the entire acceleration structure, we might find that we've run out of objects to check against. So then we ask ourselves, do we have a hit? And if we do, then, or if we don't, we were going to call the miss shader. And from the last video in the series, we talked about sky models and things we might want to do with the miss shader. But if we do have a hit, then we'll call the closest hit shader, which is going to be our reflection models or refraction or some other type of thing we might want to do. This represents the most expensive thing that we're going to do. The whole time, we can use something called a payload to help us keep some constant state going, and we can modify it as we go through each of these shaders. And this kind of acts like a global variable. So let's talk about any hit shaders. So an any hit shader is called after we go through the intersection shader. And the question that we're trying to ask ourselves is that we have a hit, what do we want to do? So we have a few options. One idea is we could do alpha testing. So maybe we have a texture map or some other way of determining procedurally whether or not this fragment is transparent or translucent, and we could say, well, maybe we don't need to keep going with this object anymore, or maybe we need to go through it. So this doesn't count as a hit. Maybe we need to spawn new rays. So maybe in this particular, we're going to talk about this as like participating media as an example of this. Another thing we could do is maybe we just need to kill the ray. In other words, if we were testing against a light source, then maybe we need to say, well, we hit the object, we didn't get to the light, so this area isn't shadow. So now we're going to talk about shadows. So let's talk about shadow rays. In particular, we want to talk about Whitted style ray tracing, where we have three important kinds of rays. One's reflection, one are refraction, and the other type are shadow rays. So let's say that we have a scene where we have a viewer, a glass object, a solid object, and two lights. So we're going to shoot a ray from the viewer to the object. And we might shoot a refraction ray going off in a certain direction. And we might shoot a reflection array that might end up going to the sky. And now we want to do shadow rays, where we're trying to determine, well, what lights are contributing to the point on that's visible to the viewer. So maybe we take this main light in the sky. So we're checking for anything in between, and we see that there's nothing in there. So we can go ahead and shade this part of the object with the illumination from this light. And now we're going to cast another shadow ray towards the other light. So we're tracing the ray, and we find out that, oh, we have a collision here. And So now we have to decide, did we make it too light? And in this case, we did not. So then we will say, well, this light is in shadow because of this object that's in between. So the algorithm is loop over every light, where shadow if we get blocked, and shaded if not. So we can ask ourselves, well, what kind of stuff is blocking? Perhaps there's a cloud in the way of that other light source. And surely some of the light gets in there, but what's going to happen is you'll have scattering events where light will be redirected other directions. So that's what we're interested in, which is what we call participating media. So let's talk about participating media. In an informal way, we can just say, well, this is the kind of stuff that scatters light. There are many examples for this. For example, marble scatters light. It's not completely solid. Milk, the reason why your milk is white is because of scattering of light. Your skin, if you ever shined a light or looked at somebody in front of a light, their ears, you can see light goes through the skin. And finally, painters would consider aerial perspective. In other words, further objects away would look bluish because of the atmosphere effects. So when we're talking about scattering, we can be referring to one of two things. It could be isotropic. In other words, scattering is even magnitude in all directions. Or we could be talking about anisotropic. In other words, the scattering could be different magnitudes in different directions. We can also do some further classification, and there's four main types. One's called absorption, emission, inscattering, and outscattering. So let's just say we have a participating media event, and we have an incoming ray. So we might say that this ray has a certain amount of magnitude, so we'll just shade that in. And absorption is when you get less of the light out than you got in. And emission might be you got in some light, but you ended up getting more light out. So maybe there's some kind of reaction to light in this particular case. The third kind, inscattering, happens when you have a ray of light coming in, but it's being affected by light that's also incoming to the same direction, or the same point. So we would say that inscattering then increases the magnitude of the ray coming out. And then the last one, outscattering, happens when you have a certain amount of light coming in. However, that light, instead of incoming light, we have outgoing light. And so then what happens is that we have less light coming out in our original direction. And that's called outscattering. And there can also be some different complications. For example, the light may change phase as it goes inside the participating media, in which case we'd have to simulate cancellation due to phase. Or perhaps you have white light coming in and you have to think about it spectrally. In other words, you have red light, green light, purple light, all different kinds of light that you also have to handle specially. So participating media can be challenging, but if you look at the kinds of effects you can do, whether it's representing marble or milk or skin, aerial perspective, and so on, even the beams of light that you see coming off of shadows due to the sun, those are all types of things that participating media are good for. And in the context of any hit shaders, we need to think about what could happen. So let's take a look at that. So for instance, we might have some kind of participating media, maybe it's a cloud or something, and if you have an incoming ray going into it, then what you end up having are probabilistic events. So maybe we say it's able to travel a certain distance before there's a scattering event. And let's just say you can model some of that scattering by introducing new rays. But then you could also say, well, let's keep going along the ray. Maybe there's a certain probability that it's able to travel some more, and then maybe it itself gets scattered in another direction, and we can no longer continue in that direction. And so this is one form of handling participating media, where you just kind of handle events of what's the likelihood that it keeps going, what's the likelihood that it stops, what's the likelihood that it goes in a completely different direction, or perhaps maybe we want to model several different directions. And along those rays, then you might want to have further events. For example, does it keep going and eventually make it out of this media or not? And so as you can tell, participating media can be a bit of a challenge when it comes to doing this real time. However, knowing how this works is sometimes helpful in recreating these particular kinds of effects. For example, if you're doing skin, sometimes you want to come up with a model, because what's happening is as you have light coming in, it might take an indirect path and then eventually come out somewhere else. And so, or maybe it's going, you have a certain thickness to it, and then some of it leaves the other direction. So sometimes you can kind of create some type of mathematical model to this, which can be helpful to do this real time. So not everything has to involve a huge branching factor and so on. So with that, let's just wrap up what we've taken a look at. So by way of review, we took a look at the ray tracing pipeline. We talked about anti-hitch shaders and how we can use those to accomplish several different things, from alpha testing or spawning new rays or even discarding rays. We talked about how to use shadow rays to do illumination or determine if objects are blocking. And lastly, we talked about, well, what if the stuff that's blocking isn't exactly some solid object or a perfectly reflective or refractive surface? And we talked about that with participating media. So I'd like to thank you for watching the video and tell you adios.